So, yeah, a few hiccups with information transfer, so bear with us. But I'd like to open the session by giving details of the ICAS Award for Innovation in Aeronautics and our awardee. Then we have an acceptance video, all will be explained, and then one of the awardee's colleagues is going to deliver a presentation. So let's introduce the ICAS Award for Innovation in Aeronautics. I feel like I'm being eaten by an ant here. The purpose of the award is to recognize contributions of an individual or a team in effectively integrating a suite of advanced technologies combined with new design and/or manufacturing processes to create a new aeronautical system with significant worldwide impact. The awardee is Helen Weber, Dr. Helen Weber of Reaction Engines, who is at the moment on maternity leave. So Helen cannot be with us today, but she has prepared a video message. So just to go through Helen's achievements. Helen joined Reaction Engines in 2005 and was awarded a PhD in aeronautical engineering sponsored by Reaction Engines in 2011 after studying the enhancement of the aerothermal performance of pre-coolers for high-speed air-breathing engines. Her PhD required the design and development of an ultra-low-speed transient heat transfer wind tunnel to carry out low Reynolds number heat transfer studies. On completion of her PhD, Helen worked in Reaction Engines as an engineering project lead, initially on the Advanced Nozzle Program supporting development of the Sabre air-breathing hypersonic engine. Then, from 2014 to 2016, as the Performance and Aerodynamics team leader for the whole engine. In 2016, she was appointed as the engineering project lead for HTX, the development, build and test of the first Mach 5 equivalent ground test demonstration of a Sabre pre-cooler. She led the design and build of a pre-cooler capable of surviving air temperature gradients of 850 Kelvin, air inlet temperatures of up to 1250 Kelvin, and tube wall temperatures above 950 Kelvin, together with the ancillary equipment needed to demonstrate the cooler's successful operation at scale. She led the team as they overcame very significant manufacturing challenges associated with brazing over 30,000 joints to be leak-tight against high-pressure helium. She re-engineered a helium circulator pump after initially unsatisfactory design by an external contractor, and assembled and conducted a dry run of the whole system in the UK, covering every aspect except high-temperature air, before shipping it out to Colorado for the full test. The first test run in March 2019 proved highly successful, with every parameter being within 5% of its predicted value. This allowed a rapid ramping up of test conditions to the equivalent of Mach 4. In October 2019, under Helen's leadership, the team successfully demonstrated the pre-cooler at Mach 5 equivalent conditions, quenching airflow temperatures in excess of 1,000 degrees Celsius in less than 1/120th of a second. So throughout her time in Reaction Engines, Helen has developed her knowledge to set Reaction Engines apart in its understanding of how to make high-speed air-breathing engines feasible. She has proven to be an outstanding leader, coaching and mentoring her team members to fuse them into a high-performing unit, who've delivered several world firsts and put Reaction Engines at the forefront of high-speed aerospace propulsion. In parallel, she has acted as an outstanding exemplar for young engineers, giving numerous presentations at Royal Aeronautical Society and other events, and giving generously of her time to promote STEM in schools and colleges. She has made an outstanding contribution to the advancement of high-speed flight and space access, and is a worthy recipient of the 2024 ICAS Award for Innovation in Aeronautics. We please mark Helen's achievements in the usual way.
Good news is we have the slides, bad news is we don't have the video.
Okay, so I'm now going to ask a colleague of Helen's, Richard Varville, to come and present this morning's presentation. Richard graduated from Bristol University in 1983 with a degree in mechanical engineering. He completed his apprenticeship at Rolls-Royce before joining the Advanced Projects Office, working on various military gas turbine concepts, including the EJ200, responsible for design work on Hotol's RB545 engines in the late 1980s, and then left Rolls-Royce in 1990 to co-found Reaction Engines Limited, together with Alan Bond and John Scott. The founders then conceived and analysed a new SSTO spaceplane called Skylon and its propulsion system called Sabre, which overcame the main engineering problems experienced by the Hotol aircraft. Following significant inward investment and growth in the company, this finally resulted in the practical demonstration of a lightweight, frost-controlled pre-cooler in 2012, which solved the key obstacle to realising the Sabre engine concept. This achievement caused the UK government to reverse its 1970s decision to withdraw from launcher development. Anybody who persuades the UK government they've made a mistake is a major achiever, in my view. So the UK government then decided to invest in the follow-on air-breathing demonstrator engine. This demonstrator has now passed its CDR and successfully tested all its main subsystems. As of 2023, Reaction Engines employs 250 staff, and apart from space, is pursuing interests in high Mach flight and spinning off the heat exchanger technology into adjacent fields such as aviation, motorsport, and general industry. So, thanking you all for your patience. Richard, can I now hand over to you?
Well, good morning, everybody. Chris has given a very good summary of my talk, so I barely need to deliver it anymore. Is the slides coming up, or? I'm sure I need to press this or what. Okay. So I gather that the PowerPoint's still on its way. So I'll try and talk for a few minutes without any cues. So as Chris explained, a long time ago, when I didn't have any grey hair, I was working at Rolls-Royce on a project called HOTOL, which stood for Horizontal Takeoff and Landing. Not a very exciting name, I know, but it was a very exciting project. It was really the UK's first attempt to design a proper single-stage to orbit spaceplane that could take off from a runway, fly into space, deliver a payload or collect one, do a re-entry and land back on the same runway, and then do it all again the next day. Oh, fantastic. Here we go. So that was a fantastic project, and it's one of the best periods of my life. But sadly, like a lot of British projects, it was then cancelled for not really very good reasons. And myself, along with a couple of other of the key engineers at Rolls-Royce, decided that actually that was a real mistake, and that we wanted to try and progress the project and progress the technology in the hope that one day it would be picked up by general industry and taken to completion. So I left Rolls-Royce and we set up Reaction Engines. We're talking about this is sort of 1990 now. And as I said, the long-term objective was to usher in a new era of single-stage to orbit launch vehicles that were cheaper, more reliable, more responsive, and operationally a lot simpler than expendable rockets. Now, obviously, that's a very easy thing to say, but much harder to do. The problem being that such vehicles are not possible with pure rocket propulsion, even when you use the best propellant combination you can think of, which is LOX hydrogen. LOX fluorine is not practical for obvious reasons. And the reason is that such vehicles can't be built with rockets is that their fuel consumption is too high, so their specific impulse is too low. And also the structures technology is not able to make the vehicle structure light enough to make that possible. So the idea behind the propulsion systems that we've been working on then is to come up with a high Mach number air-breathing engine in order to use atmospheric air for propulsion during the early phase of the ascent. Now that's not a new idea, of course. But the idea is that by replacing the liquid oxygen with air, which you can use both for reaction mass but also oxidizer to burn with the fuel, you can actually increase the specific impulse, i.e. reduce the fuel consumption, by about a factor of 5 during the early phase of the ascent. And then because of the nature of the rocket equation, even though air-breathing propulsion may only get you to Mach 5, I say only, which is like a fifth of the delta V needed to get into orbit, because of the exponential nature of the rocket equation, it has a disproportionate effect on the overall mass ratio of the vehicle and enables you to reach orbit. Now, as I said, that is in itself not a new idea, but the problem is that the normal air-breathing engines that you can think of for doing that mission don't work. And those could range from things like gas turbines, of course, ramjets, scramjets, turbo rockets, or more exotic engines like the liquid air cycle engine, LACE, and others. And they all fail for one reason or another, either due to their limited Mach number range, as I said, you really need to get up to Mach 5, or they're too heavy, or in the case of the LACE engine, they burn too much fuel. In fact, their fuel consumption is not that different to a rocket. So our propulsion system, which we call SABRE, uses liquid hydrogen fuel, which you're going to need for the later rocket ascent anyway, to enable the high Mach flight because of its incredible heat capacity. Now, obviously, hydrogen's got a very good calorific value, nearly 3 times that of kerosene, which is great, obviously, for any aerospace propulsion system. But in this case, its unique property is the fact that it's super cold, down at 20 degrees Kelvin in the tank, but also has a very high heat capacity due to its low molecular weight. In fact, hydrogen can absorb about 15 times more heat per kilogram than you can with kerosene. And that is a key property that you need to enable high Mach flight. And as it says at the bottom there, obviously with this incredibly demanding sort of technical objective that we've set ourselves, there is lots of potential for innovation, and there still is. So Chris mentioned that back in the day there was a project called HOTOL, which was a Rolls-Royce British Aerospace project. And as I said, this was really the UK's first attempt to have a go at solving this problem. And that image on the top right is where we ended up. But being a first of its kind, it suffered from a number of problems. And in particular, we belatedly realized that we'd actually got the engines in the wrong place. If you like, this vehicle was a rocket, where obviously the engines are on the base, sort of tipped on its side. And because the engines are a very significant fraction of the dry weight of the aeroplane, that meant that the wings had to be at the back as well. And that, we belatedly realized, gave rise to an awful lot of problems. And when we set up reaction engines, this was really the key problem that we had to solve when we came up with the Skylon concept, which is on the bottom right there. And as you can see, what we basically did was to take the engines off the fuselage base, put them on the wingtips, and then slide the whole assembly forward. And with one bound, Jack was free. That suddenly, instead of fighting us on every front, the aircraft actually started to work with us, and it helped us solve other problems as well. And really, the project never looked back when we made that one key change. And as you can see, there's a lot of other minor differences as well. For example, the hydrogen tank, which is the big red object, is split in 2. There's now 2 tanks, one at the front, one at the back. And by scheduling the fuel consumption during the ascent, you can actually get the center of gravity to roughly follow the center of pressure movements. And you can get the vehicle to very accurately trim itself during the whole ascent and re-entry. Now that's very easily said, and I can tell you it's taken hundreds of hours of detailed modeling to actually prove that. And there's a lot of nuances beyond what I've just said around that. But nevertheless, it did allow us to solve that key problem. And then along the way, we solved other problems as well that HOTOL had run into. Structurally, it wasn't very efficient. It had some very exotic materials, which were more on a sort of a wing and a prayer than were practical. And even now, some of those materials have not been realized. Anyway, so in the course of redesigning Skylon, we solved all those problems, and as I said, we now have a viable concept. So a little bit more about Skylon. As you can see, it's got its payload bay in the middle there. That payload bay could either carry an inert payload by itself, or it could carry an upper stage with a payload. So the vehicle could be used in a two-stage to orbit mode as well as a single-stage mode. And that's incredibly important because despite the use of air-breathing propulsion, the vehicle is still sensitive to mass growth. Well, what aeroplane isn't? But nevertheless, this is more sensitive than normal aeroplanes. So by using an upper stage, you can counter that mass growth sensitivity and increase the payload. The design objective is 15 tons to low Earth orbit in single-stage orbit mode, which we are close to at the moment. A reusability of 200 missions per vehicle. Obviously, far less than aeroplanes, but a lot more than one, which you'd get with an expendable rocket. A marginal launch cost of about $15 million a flight at low rates, which would fall to about $1.5 million at high flight rates. LOX hydrogen propellants, as I mentioned earlier. So the abort rate is a key property. As you know, rockets are the most dangerous form of transport known to man. The loss rate is about 10 to the minus 2. Which is 5 orders of magnitude worse than civil aviation. So with a vehicle like this, we're looking to sort of split the difference. So we'd like to convert the expendable rocket loss rate to our abort rate. And the reason we think we can do that is we've got redundant propulsion and we can fly the vehicle back if we have an engine failure. And then that would equate, we think, to about a loss rate of about 5 10 to the minus 4. Down mass capability, so that means that the vehicle could retrieve payloads from orbit. A full abort envelope, as I said earlier, something which is taken for granted with aeroplanes, but is largely ignored with rockets. A turnaround of about 2 days in mature operations. The key parameter there is the reliability of the aeroshell and the engines. Full airworthiness certification, something that's never talked about with space transport, but is essential if you're going to get insurance and carry passengers one day. Low environmental impact, so in other words, we don't want to generate CO2, so this is a hydrogen engine. But also it mustn't exacerbate the orbital debris problem, which has been created by expendable launch vehicles. And finally, spaceport operations. So vehicles like this would take off from runways from a facility that would look very much like an airport. And the advantage there is lower noise, much safer operations, but very importantly, it means that multiple vehicles can be serviced in parallel and then only brought out to the runway and launched when they're ready to go. So just like an airport, you could in principle support over 100 airplanes operating from one facility. So what about the propulsion? Well, we call this SABRE, synergistic air breathing and rocket engine. Bit of a mouthful, but SABRE rolls off the tongue quite easily. It's a LOX hydrogen propulsion system in rocket mode and hydrogen in air breathing, specifically designed for this role. It is not really much good at doing a cruise mission. And the image you see on the bottom left there is an earlier variant of SABRE, which was a fully integrated air-breathing rocket engine. So the way this worked was that the air-breathing engine had a very, very high pressure ratio and actually pumped the airflow into the rocket combustion chamber, which you were going to use for the later ascent. So that's a very highly integrated engine. The latest variant of SABRE actually is far less integrated and is in fact 2 separate engines and has been designed for higher performance, but more importantly, lower complexity and lower development cost. The engine you see there on the left is pretty exciting, I will admit. Has some rather demanding technology in it, which we've now found a way around. As it says at the bottom, most of the technology is now demonstrated at proof of concept level, and the pre-cooler, which I'm going to talk about in a minute, is TRL5. So what's this pre-cooler all about? Chris mentioned it earlier about Helen's award, but the problem with flying really fast in the atmosphere is that the air gets hot. As you know, the recovered air temperature increases with the square of the Mach number, which is just, all that means is that all the kinetic energy that you've acquired as the air gets slowed down in the inlet is converted into heat. And as you know, that depends, it's c squared on 2cp. So that goes with the square of the Mach number. So to make an aeroplane like this work, you really need to get up to about Mach 5. A lower Mach number is not good enough. So at Concorde speeds, Mach 2, the recovered air temperature going into the front of the Olympus engine was about 100 degrees C. With this engine at Mach 5, the recovered air temperature is 1,000 degrees C, which is sort of twice the melting temperature of aluminium. So it's literally too hot to handle. So the idea behind the pre-cooler is you use the heat sink capacity of the hydrogen fuel, which you're going to burn later in the engine, to actually cool the airflow down to a temperature where the air compressor can tolerate it. So that means at Mach 5, cooling the air from, let's say, 1,000 degrees C down to some low temperature, and this depends on the particular variant of Sabre that you're looking at. It could range from sort of ambient down to maybe a cryogenic temperature of minus 150 in about 1/100th of a second. And that's going to entail transferring about, 400 to 500 megawatts of heat. And the mass budget that we've set ourselves for that is about 1.5 tons. So how on earth do you do that? Well, it turns out the best way to do it is to arrange the heat exchanger into a cylinder composed of thousands of small diameter tubes, about 1 millimeter diameter, arranged in involute spirals. So what happens, if you look at that image there, the coolant arrives on the inside of that heat exchanger and spirals its way outwards, whilst the air flows radially inwards in cross-flow over the tubes. So that gives you the best of both worlds. It gives you a heat exchanger that's got low frontal area, so it gives low drag on the aeroplane. It's in thermodynamic counterflow, so it's very efficient, about 95%. But because the air is in crossflow, it gives you high overall heat transfer coefficients to minimize the surface area. And there's lots of other cunning features about it as well. In particular, it has full thermal expansion accommodation. So often, to my amazement, people design heat exchangers without actually accommodating thermal expansions and then get a little bit surprised when they crack. In this case, you have to accommodate thermal expansion because the tubes increase in length by about 10 millimeters when you're running at Mach 5. And the way we do that is we anchor if you like, the inside of the pre-cooler, and we allow the outside of the pre-cooler to rotate slightly relative to the inside, and that allows the tubes to expand. Anyway, so on paper, it all looks brilliant. What's the actual problem with doing it in practical reality? Well, there are two main problems. One is how on earth do you make it, because you've got to make thousands of leak-tight joints. This thing runs at a couple of 100 bar, and it has very thin tube walls. So how do you actually do all that brazing successfully? And then the other issue is frost control. So as I said, with some of our Sabre variants, we cool the air sub-zero, and that gives rise to an issue of frosting. So what about this frost control? What's that all about? So as I said, if you cool the air sub-zero, what happens is that any water vapor in the air immediately condenses from the vapor directly to frost without going through a liquid phase, and it blocks the pre-cooler matrix in about 3 seconds flat. And I know that because I've done it. So you have to have a frost control system to prevent that. And the way we do that is to use an antifreeze, which in our case is methanol, which mixes with the condensed water vapor and keeps it as a liquid. So you've actually got a two-phase, effectively it starts raining inside the pre-cooler. But it's not quite that simple, because if you just inject the methanol and let it run through the pre-cooler, the consumption of methanol is very large. So what you have to do is actually catch the condensed liquid and then recycle it in a counterflow direction to the airflow, which is in fact extremely difficult to do. So we need liquid separators inside the pre-cooler, which are running at airflow velocities about 5 times higher than standard industrial separators, but also have to operate upside down and in adverse G. Anyway, so that is tricky. And we've done quite a lot of technology development on that over the years. And you can see on the bottom left, there's a little wind tunnel where we developed that technology. And the graph in the middle shows that we got it to work. And then having got it to work in the lab, we then did it at a representative scale. And you can see the facility on the bottom right there, where we have a pre-cooler, which in fact I think is on the next image. So if you see that image on the left there, that red ring is just in front of a pre-cooler, which is just about there, of which a larger image is here. Sorry, here. So that is the pre-cooler. And as I said, it's got the frost control inside it. And this experiment was done around 2012 and used high-pressure helium as the coolant. And in fact, the way it worked was, we had a large tank of liquid nitrogen here with a coil inside it. So we had high-pressure helium was being cooled with liquid nitrogen, and then we had a helium circulator here. It was then sent into the pre-cooler where it cooled the air, and then it came back and was recooled. So the helium was in a closed loop. And after a lot of messing about, we got that to work. So this image here is one of the examples. So this graph here shows the air coming in here, and then we're switching the helium into the pre-cooler, and the air temperature plunges down to this level and then stabilizes at about minus 120, I think, in that particular example. And then we ran it for several minutes until we got bored, and then we turn the helium off, and the whole thing warms back up again. So that test really got us on the map. And as Chris said, it had all been, amazingly enough, the entire project had been funded through private investment up to that point. We'd had no grants or anything like that, or assistance. And, but nevertheless, having got that to work, it got us on the map. And that really changed the UK government's attitude about the project. In fact, there is a little video of the thing running. That's actually looking inside the pre-cooler. So what's happening is that the air is coming radially in now. It's very cold. As you can see, it's formed this cold vapor cloud, and then it's turning into the axial direction. And there's actually a jet engine that you can't actually see about a meter downstream of that is sucking the air through the pre-cooler. So that was pretty exciting, and as I said, that changed the UK government's attitude to both the company and the feasibility of the technology. And that previous test was just taking an ambient air and cooling it down to cryogenic temperatures, so it was only addressing part of the temperature range. So what we did next was to build a new facility in Colorado where we addressed the high temperature end. So this was rather similar. So this used another jet engine, which in this case was a J79 in that shed there. J79 was like a sort of second generation turbojet engine used in the Phantom and Starfighter and things like that. Anyway, but in this case, the engine was running on full reheat, and it was discharging hot air into this plenum here, large stainless steel cylinder, and then we were tapping off from that, and it was going down a pipe into this building here, where it was then being received by the pre-cooler. So what was happening, this is an exploded version of the facility, but the hot air was coming in here, it was then flowing radially out, and then radially back in through the pre-cooler, which you can just see there. The whole assembly has been split apart in this picture. So it was taking in 1,000 degrees C air here, cooling it, and then sending it back into the axial direction. And in this case, we weren't using liquid nitrogen as the heat sink, we were using water, boiling water in fact, so it was cooling the air down to about 100 degrees C. But otherwise very similar, so using helium at 200 bar as the actual heat transfer medium in the actual pre-cooler. So so we've now covered the entire temperature range of the pre-cooler, and in fact, that was the subject of Helen's award, this particular experiment. So that was pretty good. So I was just going to, the title of my lecture is sort of a bit of innovation in general at reaction engines, so just talking about a few of the other things that we've done along the way. So the engine I showed you, Sabre, has a particular challenge because it starts off in air-breathing mode and then ends up in rocket mode. So effectively, you've got these two different engines with two different nozzle systems. And as you know, rocket engines have very large diameter nozzles in order to maximize the exhaust velocity, to maximize the thrust and minimize the fuel consumption. So during air-breathing mode, you've got this very large rocket engine effectively sitting there in the nacelle doing nothing. And that gives rise to a particular base drag challenge. And in fact, the various Sabre engines over the years have been specifically conceived to try and address that challenge. And that's resulted in varying degrees of sort of air-breathing rocket integration. And with the first Sabre engines, they were completely integrated. So the air-breathing engine was actually using the rocket combustion nozzle during air-breathing mode, which required a very high pressure ratio air-breathing engine. But nevertheless, the flow was still massively overexpanded in air-breathing mode, resulting in a degree of flow separation inside the nozzle. So over the years, we looked at various other approaches to that problem, and that resulted in quite a lot of sort of design analysis and testing of various different altitude compensating nozzle concepts. And you can see these images here of different, I keep pressing the wrong button, different experiments over the years of different types of altitude compensating nozzles. This is a full what's called expansion deflection nozzle, so that you can't quite see it, but there's a pintle inside the nozzle here, a bit like a mushroom valve, that sends the flow radially outwards into the skirt downstream of the throat, so that the flow from the engine comes out as a thin annular jet whose thickness varies depending on the back pressure. So we've done quite a bit of testing on that, didn't quite do what we wanted, and this was a later engine and so on. And then in the later variants of Sabre, we actually reduced the air-breathing pressure ratio, and you can't quite see it here, but the air-breathing flow was actually designed to come out downstream of the rocket engine throat through an annular throat here, and you can just see the edge of it there. And we've tested, as I said, quite a number of different concepts. And this is a very difficult problem, I will admit. Anyway, to be honest, in the end, we didn't like any of those nozzle concepts. And we've got a new idea now that we're working on, but it's still a work in progress. But I am hopeful that that will be the ultimate answer. So Chris alluded to the fact we've also been working on a more integrated demonstration engine for Sabre, which we call Demo A for air breathing. And this has involved designing and testing quite a number of the other subsystems in the engine. And that's entailed hydrogen air preburners using micromix approach, which you can just see in this image here. It's a micromix combustor. So each one of these is actually an air port, which has a hydrogen jet with transverse injection and mixing, and then stabilization of the flame downstream of the injector plate. So we've designed and tested those. They work pretty well. We've looked at other heat exchangers associated with heating the helium loop at low Mach numbers for the earlier Sabre engines, which we call HX3. We've also looked at, we've done integrated tests of that preburner with its heater. We've done control system simulations and so forth. We've also done tests of the heat rejection system from the helium loop, where the helium loop rejects the waste heat to the liquid hydrogen, which is yet another heat exchanger type. In this case, it's a microchannel heat exchanger, and so on and so forth. So we've done a lot. So that's the story on Sabre. Of course, like all companies, we have to earn a crust somehow. So we developed a lot of technology, and we've been looking in recent years at spinning that off into other sectors in order to get an income. So nowadays, the company is really split into sort of three areas. So the first is the Sabre sort of space access piece that I've just been describing. The second area that's closest to Sabre is what we generally called high-speed flights. This is high Mach number cruise flight for various missions using Sabre-derived technologies. And then the third piece on the right is spinning off, in particular, the heat exchanger technology into other sectors that are further afield from Sabre. So first of all, on the hypersonics side, we've been working on a project called HVX, which is funded by the effectively the Royal Air Force through an outfit called the Rapid Capabilities Office. And this we've been doing with Rolls-Royce, where we are in fact priming this project. And that is looking at an engine that is similar but different to Sabre, but also uses pre-cooler technology, and is quite an important project in the UK. Being a military project, sadly, I cannot tell you too much about it, though. So on the heat exchanger spin-off side, we've been working very hard looking at various different sectors. Probably the most adjacent sector is civil aerospace. Of course, civil aircraft don't have quite the same thermal management challenges as Skylon, but nevertheless they do have various heat exchangers for cabin air cooling and all the rest of it. But of course, the drive towards sustainable aviation, as it turns out, really does have some quite difficult thermal management problems, in particular hydrogen fuel cells, whereas you know they might be, let's say, 60% efficient, but sadly that means that 40% of the chemical energy you've converted into electricity actually results in waste heat that is left inside the fuel cell itself. I mean, obviously with a normal jet engine, the great thing is all the waste heat just goes straight out with the exhaust and you never see it again. But in the case of a fuel cell, it's actually left inside the cell itself and you've got to get rid of it. And that's quite a challenge, actually. So that image on the top right is a fuel cell cooler, where ultimately you're dumping the heat from the fuel cell into the air via a liquid coolant loop, generally water with a bit of antifreeze in it. And as you can see, that's another spiral heat exchanger, very similar to the Sabre pre-cooler, using all the same principles. So that we're working on hard, and we're working on various projects with companies like Cranfield Aerospace on a project called Fresson, and with various others as well on that. So that's the story on civil aerospace. And then we've also found ourselves in motorsport a little bit. So we're actually supplying more than half the F1 grid now with intercoolers. So these are, again, small spiral heat exchangers about the size of a large Coke can, which are taking the turbocharger delivery air and cooling it before it goes into the engine. But also looking at various other heat exchanger issues. As you know, there's a move towards electric vehicles and maybe even hydrogen fuel cells, those same problems there, and battery cooling. So electric vehicles I've just mentioned. We are working on a product which is designed to, without active pumping, remove the heat from battery cell packs, and so on and so forth. And then also we're working on more industrial applications like waste heat recovery for net zero and so forth, which, as you would expect, are not quite as exciting applications, but nevertheless important. And sometimes those result in what we call straight rack architectures, where the tubes are just straight and the thing's not arranged in a spiral at all, but it's arranged in a sort of multiple rack that you can stack up. So that is most of what I had to say. The most recent sort of test that we've just publicised a couple of weeks ago is we have in fact done a ground test at Mach 3.5 conditions of an integrated pre-cooler with its jet engine in the UK, and there's a couple of pictures there. And we're not just doing that, but we've also got a high Mach intake test underway and other technology testing. So that really is the sum total of my talk. Thank you.
So thank you very much, Richard, and apologies again for the delay. So you'll be hanging around for a coffee and maybe answer some very learned questions, but for now I'd like to invite our President Dimitri up for present the medal for Richard to accept on Helen's behalf.
See, there's a picture over there. So.
Can I also invite the members of the local organising committee up to also a gift for Helen?
Thank you very much.
So before you shoot off for the coffee break and to question Richard about this very exciting technology, can I just remind you all of the interactive session that will take place at 10 o'clock after the break. And Ricky has asked me to make a couple of announcements. We still have some interactive authors who've not uploaded their their digital version of their presentation, their poster. Okay, so just to confirm, this is not a paper poster, this is an upload. So he's asked me, for those of you who are presenting in the interactive session or have friends or colleagues or students presenting in the interactive session, is please ask for you to check, or for them to check, that their paper is actually uploaded on the monitor. Now, you find out which monitor by going onto the app, going to the interactive paper sessions, find your paper, and the app will explain which monitor it needs to be uploaded to. We have 12 monitors and obviously 17 tracks, so there isn't a correspondence between the track and the monitor. So can interactive authors please check the monitor and then go and make sure that their presentation is actually uploaded. Axel, do we have any other housekeeping announcements for today? Okay, so just remains for me to thank you all for your polite attention and for your patience this morning, and thank Richard for speaking, and above all to congratulate Helen for being a role model for young and female engineers, and to congratulate her on extraordinary achievement and this ICAS award.